simultaneous meeting to this computer. I don't know where it's recording to, but I guess I will find out after it's over. We'll figure that out. All right. Didn't give me an option on where. So, um, 3.1.0. So an automatic air conditioning circuit is simple in nature and is a good place to begin an analysis of control circuits. Figure 40 shows a very basic cooling system control circuit. Power from the power plug is applied to the on-off switch. When the switch is in the on position, power is passed to the cooling thermostat. When the thermostat calls for cooling and closes, power is passed to both the compressor and the fan motor, causing both motors to run. When the thermostat is satisfied and opens, the motors lose power and shut off. This describes sequence of operation for this circuit. So figure 41 shows a control circuit that is more typical of a basic comfort cooling system. Some additional features have been added to this circuit. A transformer has been added because 24 volts is required for the control circuit. This makes the control circuit components and wiring less expensive and easier to install. An indoor fan motor has also been added to the circuit because the control circuit is now operating at 24 volts. The control relays C and indoor fan relay IFR are added to provide control for the motors. The following is the sequence of operation of the circuit as shown in figure 41. So the circuit shown in figure 41 is going to be very typical of a cooling only system with an air handler with no electric heat, right? So if you're talking residential, you're talking a system that probably has a boiler for heat or something like that. Um, if you're talking commercial, you're just talking a single space that requires cooling only, so you go with an air handler. Obviously, if you have a furnace, the control circuit will end up looking a little bit different. Um, the indoor fan relay can be a little bit more complicated than what they show, depending on how they choose to control the indoor fan, but that's the simplest way to do it. And honestly, there's nothing really wrong with it except for you got no time delay. So that is a very good typical cooling system control circuit. So that's usually the best place to start. If you've never done troubleshooting, you can make sure you know how everything's supposed to operate in that and then build up from it. So starting at the bullet points for the sequence of operation, line voltage is applied at terminals L1 and L2, making it present at the contactors C. The indoor fan relay, IFR, in the primary of the system transformer at all times. When the transformer energized, the 24-volt output from the secondary is applied through one control circuit path to the on terminal of the fan switch and by a second control circuit path to the thermostat on-off switch. When the fan switch is in the on position, power is applied through the first control circuit path to the coil of the indoor fan relay, energizing the relay. This causes the related indoor fan relay contacts to close, applying a line voltage to the indoor fan motor and causing it to run. This mode of operation allows the occupant to use the indoor fan for ventilation without operating the compressor for cooling. Some occupants will allow the fan to operate continuously even as the compressor cycles on and off to cool the structure. With the on-off switch closed, the thermostat calls for cooling, and the fan switch is placed in the auto position. Both contactor coil and indoor fan motor are energized. This causes compressor, outdoor fan, and indoor fan motors to be turned on simultaneously as required for the cooling mode of operation. Most users with a cooling-only system choose to allow the indoor fan to cycle on and off with the compressor. So, side note, just because I want to bring it up, it's something I've actually learned semi recently. So, if it's something that you've known for a long time, well, then I guess you paid more attention than me. Interesting note while we're talking about on and off, just because I don't know if it'll come up again. Um, if you leave the fan on, especially if you're not talking about a system that has multiple fan speeds for fan on and for fan on with cooling, you know what I mean? So continuous fan, a lot of ECM motors have a continuous fan that's something like 40%, 30 or 40% of standard speed, and then it ramps up when you need cooling. And then communicating systems um, will have a a startup period where it runs at a lower speed on the fan to try and dehumidify before it lower sensible temperature. If that's a little bit too much for now, don't worry about it too much. But what I'm trying to get at is leaving the fan on instead of putting it in auto in cooling mode um, tends to raise the humidity of the structure because you re-evaporate water off the coil. So if you're having humidity issues, like they're trying to keep it at 50, 55% humidity and it's running 65%, if they leave the fan on, try moving that to auto. Same thing could go for commercial systems. If you're trying to control humidity in an environment and it's cycling relatively frequently, it may help to switch that to auto if at all possible, depending on the system, to lower that humidity down a little bit. So it's just something to keep in mind. I have actually seen a few people solve some mild humidity situations like that in the last year or two. Um, so on isn't necessarily a good option in cooling. It's generally a perfectly fine option in heating. Um, so anyway, the basic sequence of operation for this AC is real simple, right? Um, First thing to remember on your sequences of operation is you have to have high voltage at however many units you have. So if it's a package unit, you have to have high voltage to the unit. If it's a split system, you have to have high voltage to the indoor and the outdoor unit, right? And it's got to be proper voltage plus or minus 10%. Your high voltage fuses and breakers have to be good for that to happen. Power to the low voltage transformers has to be there with low voltage output at plus or minus 10% of the rating. If you get outside of plus or minus 10% on your control side for whatever reason, then a lot of times your contactors won't close properly or they're chatter off and on, especially if you start getting to about 25% out. And if it's 25% too high, um, you're going to start to burn stuff up. Low voltage fuses have to be good. Power and control wires have to have good connections on everything. And generally any external safeties have to be closed. So if you got float switches, duct smoke detectors, anything like that that gets added after the system, that's usually going to just cut power to the unit or cut control voltage to the unit. In case of float switches, it might only cut cooling, but it depends on the system and who put it in. Generally, I try to just go cut all low voltage on an external safety and just call it that. But different guys have slightly different methods. But the point is, if there's any external safeties to the unit that are out, then you're shit out of luck too. So um, make sure that all that external stuff looks good first, especially if you have no control voltage or you have no line voltage or something like that. Check for those things, fuses, all the basic stuff first. It seems like common sense, but especially if you're in the heat of trying to figure something out and something happened later, something just doesn't make sense, whatever the case may be. Um, a lot of times you'll be missing that first thing. Is your wire actually in good condition? You'll have a system that you go to try and turn it on and it'll all run for a split second and then stop and everything looks good, and it could be a crappy wire, something like that. So if everything just seems out of whack, start with those basic things first. Always go back and just double triple check. Is the power wire good? Does it go from A to B? Is the breaker in good shape? It's not tripping as soon as it tries to run. Are the fuses good? You don't have any what looks like shorts or black marks everywhere? You're keeping power at your low voltage transformer. When the low voltage transformer calls for cooling or heating or whatever, does your voltage stay at 27 volts on the terminals? It should stay at 24 volts on. You know what I mean? Um, does it stay right there at 24 volts the whole time? Because sometimes if you got a bad wire on the control side, you'll actually start at 24 and then drop down to like 13 or 12 or something like that if you got a bad common connection or a bad wire. So just watching those things operate as you're trying to troubleshoot something will usually get you through about half of the weird ones. So never forget those first few items. You know, line voltage is good, low voltage is good, power stays at rated voltage, low voltage power stays at rated voltage, and no external safeties are screwing with you. That's the first thing that you make sure looks all good. Any questions on that? I will try and put this stuff, like I said, I want to put together some of my own sequences too, because I'm trying to work on that anyway. So I'll try and have like a little paper that I'll give to you guys that'll show that as well, so that you don't have to just re-listen to the video to hear that. But that's right, basically rule number one in that stuff. Um, so after all that's good, basically with an AC, it's just a matter of let me see if I can pull my little sequence up real quick. It's just a matter of um, obviously on AC startup, another thing to keep in mind, I don't think it mentions it here. I think it mentions it on 3.2.1 cooling sequence of operation. But if you got an electronic thermostat, it's probably got some kind of compressor protection in there. So if it's ran in the last couple minutes, then you're going to have a 3 to 5 minute timer generally. It could be, especially if it's a heat pump, that timer could be 10 minutes because there's a one in the circuit board and then one in the thermostat. If you can disable the one in the thermostat, if it's got one built in the outdoor unit, that's not a bad idea. But you're going to have a few minute delay. So if that delay timer is not on, the next thing that just happens is power is sent from the 24-volt transformer to the outdoor unit contactor. If we're talking residential, right? We're going to be talking about residential mostly because it's easy to picture, I think. Um, so you're going to have 24 volts, usually yellow wire, goes to outdoor unit contactor, closes that. That kicks on outdoor fan motor and compressor. That closes the contacts on the relay, the contactor that powers the outdoor fan motor and the compressor. Then you're going to have 24 volts go through fan, either through auto and on, and that's going to close the contacts on the indoor fan relay, and that's gonna be what actually powers your fan. So that is typical uh, sequence of operation. For cooling only, right? So if you guys are looking at this picture that I got up that shows that control circuit that's in your book, um, I'll talk about this a little bit more in a minute as far as how I test some of these components on, well, we want to do that, remove the gas. Let's just talk about troubleshooting this circuit real quick because it's a pretty simple circuit to troubleshoot. So generally where I will start if I'm worried there's a power issue is I try to start at 24 volts either to the thermostat or to the indoor unit. So where I've got this picture right now. So where I've got this picture right now, I will check, do I have 24 volts at my transformer? If I have that, then I know I've got uh, power coming in. I know the transformer's good. I know I got power coming out of the transformer. And usually, depending on how the safeties are wired, I will, if I measure it at the actual terminal on the indoor unit where it goes to the thermostat, I'll know that my external safeties are closed. So even though you should really start at the beginning, and if you're, like I said, if you got a hard one, you probably want to start at the beginning. But if you start at low voltage side of your transformer, you know, if it's a commercial unit and it's 120 volt controls, start at 120, your main 120 volt transformer that feeds your main control boards and stuff. If you've got that there and you're feeding your main circuit board and everything is good at that point, then you've eliminated like 5 or 6 things right at the gate. So that's always where I've started, is right there at that transformer on the low voltage side, because that just eliminates power coming in, fuses, everything's good. Now, if you're dealing with three phase, something to keep in mind is you could have your 24 volts or your 120 or whatever, but one phase is still down. So you'll probably still want to check power coming into the unit that you have all three phases. Keep that in mind. So if you're doing single phase equipment, you check 24 volts or whatever the voltage is at the transformer and you're good, then you know that whole power circuit up to there is good. If you're dealing with a three-phase unit, check that you got low voltage at your transformer first, because that'll still tell you if you've got your primary, um, main circuit feeders in there, and then check all three phases to make sure that those are good too. That makes sense?
Yeah.
All right. So um, after you're good there, say typically what I would recommend is if you're having an individual, and we're going to repeat this a little bit on individual components. So when we talk about troubleshooting contactors and relays and stuff like that, I want to just, while we're talking about a simple circuit of operation, I want to cover checking items in a control circuit, because I didn't see that in this book, and maybe it's somewhere in here. And if it is, we'll repeat it. But in case it's not, a very, very good practice on troubleshooting is understanding this wiring diagram. All right. So if you don't read a lot of wiring diagrams, pay attention to the ones we go over tonight and try and start getting used to them. And we can go more in depth on wiring diagrams if you guys need it. But the basically your best bet is follow your sequence of operation, follow your ladder diagram on your control side, and then figure out what's going wrong at each point. You know what I mean? So if you got 24 volts here and still nothing is coming on at all, you probably want to check at your thermostat, right? You want to go over here, put your red lead on the other side of your thermostat, and make sure you got 24 volts up to the stat, okay? Because that's where everything's going to feed from there. The other option is if you're right there at the equipment somewhere, you can check and make sure you got your signal coming back from somewhere else. And we'll talk about checking those too. But what I really want to talk about is as you're troubleshooting individual components, all right, you want to keep your common lead somewhere on the common side. So this is the common side of the transformer, and then this other side is your 24 volts. So if I draw a line here, this is all, I'm going to go ahead and make it red so that you guys can see. This is all going to be, no, I don't want that line. Dang it. Set that. All right. So if you follow this, basically on your low voltage side, this is all your 24 volts, your red, right? Goes in and then it keeps going from there. You go down. This is basically your off on cooling switch, and then that goes in. So what we're showing here over here is to your fan. So this basically, you just think about it as a separate switch. Um, Fan is your common terminal on this two pole relay, and you either got it set to on and auto, um, and we'll follow the circuit in a minute. But as you're troubleshooting these components, right? So say we've got an issue where the fan isn't coming on, and you're trying to check it at the relay. All right. Do not troubleshoot to ground. No, that would be green. Do not troubleshoot to ground on your low voltage side unless your low voltage transformer is grounded. And if you're not sure, just assume it's not. You can troubleshoot the ground if your low voltage transformer is grounded to the chassis, but a lot of times, especially if it's 24 volts, it won't be. So you always want to keep one lead on common, and you'll hear it be called the hopscotch method, right? Um, Whatever you do, you keep your black lead placed on common, and then you test everything else using your red lead with your black lead always on common to make sure you're always reading voltage. Um, Unless you've gotten really good and you know what you're doing and you're really proficient at troubleshooting control circuits, you don't want to test right across a switch. Okay, because testing right across a switch will give you 0 volts, right? If you're trying to make sure you got voltage, right? So if I test, if I want to see if power is going through this thermostat, and I test across this switch to the green wire, if it's operating properly, right? Can everybody see where I'm testing voltage? If this is operating properly, you would get 0 volts right here if power's running through that switch. If it's not operating properly, you'll get 24 volts. Whereas if you just keep your black lead on common all the time, you test on this side and you get 24 volts. And then you go to the other side of your thermostat. Dang it. Go to the other side of your thermostat and test here on your green wire, and you're passing power, you'll still get 24 volts. So you know that that fan relay should be powered if you're good on ground. And then if for some reason you're still having an issue, you can move this over to the common side of your relay and check you got 24 volts across it. But if you just keep this pinned on common and all your commons are good, then you shouldn't have any issue always checking hot to common, hot to common, hot to common everywhere in the control circuit. That way, you're not looking for 0 volts here and 24 volts there, and you start getting confused because it's it will you'll especially if you check the ground. If you're checking the ground, I've seen guys scratch their heads for a long time because on like high voltage especially, you're checking hot to ground instead of hot to neutral. You can have 120 volts hot to ground and 90 volts hot to neutral. You can have 24 volts hot to ground on a transformer and then have you know uh, 12 volts hot to common. And then you can have 48 volts hot to common if you got two transformers in there and they're bucking or something. So if you're checking to ground, um, hopefully you're really proficient at what you're doing because a lot of times it can get you in trouble. And when it does get you in trouble, if you're not used to trying to use that used to using that method of um, of troubleshooting, if you're not used to keeping that lead right on common and testing everything else after it, you'll be trying to diagnose something for a lot longer period of time than is really necessary. So that's the hopscotch method of troubleshooting. I just wanted to bring it up in case your book doesn't cover it later on. That you always want to keep one lead on common or one lead on neutral. If you're doing 3 phase, you'll have to check all 3 phases at a bunch of points. But even then you want to be checking, L1 to L2 at a bunch of locations and L1 to L3 at a bunch of locations to make sure that you got all 3 phases everywhere. You always want to make sure all 3 phases are present at every location. You don't want to just be messing with one. um so with that in mind, in this basic control circuit, right, I'm going to go ahead and color out some of these wires real quick just so that we can see it. So we got all our reds, right? So if we're dealing with standard residential colors, we're going to have this. And then if it's on, actually, yeah, this should be red. So we'll make that red. And then we're following standard colors out of the thermostat cooling. This would be yellow. And I know the yellow is going to be probably kind of hard to see, but at least it's there. And then everything else is common. And then this, let me go ahead and draw a rectangle. As a matter of fact, Let me make it a text box. What this power diagram really shows is right here. This is indoor unit, or you could imagine it as a packaged unit, I guess. But for right now, let's um let's call this indoor unit. Is this right section right here? And then outdoor unit is the section above it. And obviously, if you have an indoor and outdoor, L1 and L2 will probably be separate feeds. But you know, you got a oddball electrician, maybe it'll come off the same wire, just like they're showing. It's possible. All right. So on this, if you're somewhat familiar with contactors, you'll notice that on the outdoor section, they're showing a two-pole contactor. So if we have black and red, so let me go ahead and color a red wire. Say we're running our 240 volt, right? If this is 240 volt L1, L2, um, if L2 is in red, then you'll notice that the fan relay only the fan relay only cuts off one leg of power, right? And the compressor relay cuts off both legs of power. As a matter of fact, no. The compressor, the way they've got this drawn, actually, the compressor on the contactor on the outdoor, both legs of power are cut off by these two switches right here. All right. Make sure you guys can see what I'm trying to point at. Yeah. All right. So on the compressor, both legs of power are cut by the contactor. But on the outdoor fan motor, you see all the L2s are tied together. So on the outdoor fan motor, it's only this leg, the L1 leg, that gets cut to the outdoor fan motor. And then it's the same thing for the indoor fan motor. The indoor fan motor, um, it only cuts L1 to it. So if you've got a 240 volt, if you got a single phase 240 volt appliance, it is perfectly fine, just like any other 120 volt appliance, to keep L2 on there at all times ready to go. And a lot of times it's set up like that. L2 is powered at all times, and then L1 is the only thing that gets shut off by an individual relay. But you'll see a lot of units where it cut off both phases. You'll see some three-phase motor where it cuts off two phases but leaves one powered all the time. And you'll see three-phase systems where it cuts off all three legs of power. Uh, every manufacturer has a slightly different way of laying it out with different units. Everything works, but it's okay to have one single power feed basically hot at all times and only cut the other leg, because the motor won't run if only one leg's out. Does that make sense? Um, so in this circuit, if you've got this system in auto, so we'll move this switch. This is going to be, I'll make it the actual positions in purple. All right, so if we've got this actual switch in auto, all right, so it's not on, it's in auto, then this line is going to be right here. If we've got the cooling on, um, if we've got the cooling on, then what's going to happen is as soon as this cooling thermostat closes, right, because this is going to close on a temperature rise. So as the temperature rises, this thermostat will close. And then once this closes, power will go from R in our thermostat to yellow on our thermostat. That yellow will be fed to the auto position of the fan and then supply power to the indoor fan relay. So we'll have 24 volts at that point across the indoor fan relay. Power goes on from there and also applies power to the outdoor contactor. Then we have 24 volts across the coil of our outdoor contactor. Once that occurs, if we look up here, this fan relay will close. This contactor, this set of contacts on the contactor will close. This set of contacts on this contactor will close. Then you have high voltage power to all these motors, and everything's going to run. Basically, everything happens at the same time with a AC only circuit. And then once the call for cooling's gone, basically all this stuff opens back up. This switch opens back up. There, your cooling thermostat. Once the temperature drops, that switch opens. Power is not applied to any of these relays anymore. All those contacts open, and you're good. So if you've got a situation where the outdoor unit comes on, so you've got power to your compressor and you can see it's running. You got power to your outdoor fan motor, you can see it's running. Then what? But the indoor fan motor is not running. In this circuit diagram, what are the things that could be going wrong right there? Anybody want to participate and tell me what issues you could have if the indoor fan motor is not running? Should be a pretty easy one, I would think. But
Your fan relay?
yeah, so if the fan relay is not working, then that will not allow power to go to the motor and it won't come on. What else could be wrong?
The coil could freeze over.
If the coil is frozen over, though, you'll still have the fan running, right? So right now we got a fan motor that's not running. We're not talking about troubleshooting cooling problems. But that's well, I guess let me step back. If the fan motor's not running, your coil will freeze over. So, but we know the fan motor's not running. So the point is what's causing that fan motor not to run. So one thing could be that the relay, something's wrong with the relay. Either the coil is bad or the contacts aren't properly closing. What other issues could we have?
Did we discern if we have 24 volts out of the transformer?
Yeah, we definitely have 24 volts at the transformer because we said the compressor was working and the outdoor fan motor was working. So that means we must have 24 volts from the transformer. We're powering Y. The contactor's closing for the outdoor unit, right? So when you're thinking about your sequence, that's what I'm saying. Think about, okay, if my compressor outdoors running and my outdoor fan motor's running, I already know in my sequence of operations that I must have 24 volts, that it must be going through the thermostat, that thermostat must be sending power to that yellow wire to the outdoor contactor. But I go and I see that the indoor fan is not running. So at that point, I don't have to check all that other stuff, right? I don't have to check if I got 24 volts on Y. I don't have to check if I got 24 volts at my transformer. I don't have to check that I have incoming power to the outdoor unit. We know all those things are working. So we have already figured out, yeah, could be a bad relay coil, could be the contacts aren't closing on the relay coil for the indoor fan. There's only a few other things that can be wrong. What else could be wrong?
Could the indoor fan motor be bad?
Yep, if the indoor fan motor itself is faulty, so if you check voltage across the indoor fan motor, and you've got voltage to it, so you check that real quick and you say, well, hell, it's got 240 volts, then the motor's faulty if it's not running, right? Um, nine and a half times out of 10, that's going to be the issue, especially with a small fractional horsepower motor. There's no connections that you can change there. So if you get 24 volts at the fan motor leads and it doesn't run, then it's probably electrically failed, and we can talk about how to prove that in a different class. But yep, so fan relay could be bad, indoor fan motor could be bad. What else could be wrong? All right, the other two things that could be right is we've got this wire connecting to G. So it could be that we don't actually have the 24 volts at the indoor fan relay. So we want to prove that. If something's wrong with that green wire, like that wire's disconnected or broken somewhere, we might not have power on that wire. And then the bonus one would be, if you know anything about permanent split capacitor motors, that the capacitor is bad, right? If the capacitor is faulty on the indoor fan motor, that would also cause it not to run. But basically, by understanding the sequence, you can rule out a ton of stuff really fast. Now, obviously, if this is a separate indoor and outdoor unit, it could be you don't have power to the indoor unit. So um, the way that this circuit is technically drawn out of your book, power at the outdoor unit means power at the indoor unit. So this would be like for a packaged unit. But if it was separate, you might not have L1 and L2 at the indoor unit also. So it could be that. But you know your low voltage side is all good. So no, I take that back. Since your low voltage side is all working, most residential equipment is going to have that transformer in the indoor unit. So that proves you got power at the indoor unit too. Um, so just understanding, a lot of times understanding where that transformer is too while we're there. Um, because a lot of times residential equipment, that transformer is going to be in your air handler or it's going to be in your furnace. A lot of times in commercial equipment, that transformer is going to be in your outdoor unit if it's a split system. And obviously if it's a packaged unit, it's going to be in there. But if it's a split system, a lot of times in commercial, that transformer is in your outdoor unit. So if you have everything up to 24 volts on a single phase commercial split, usually that proves everything is good at your outdoor unit. That doesn't necessarily prove you have power at your indoor unit. With residential, it's the opposite. If I got 24 volts and everything is working just at the outdoor unit, but something's wrong in the indoor unit, I generally already know I have power and everything at the indoor unit because that transformer is working. So it must be relay, fan motor, capacitor, or a low voltage problem with getting power to G, which is going to power my indoor fan relay. So we can do the same thing on the outdoor unit side, right? If I've got my indoor fan motor running, so that's working. I've got my outdoor unit, the um, outdoor fan motor is running, but the compressor's not running. What could be wrong with that if we're looking at that section of the picture? So we got this compressor motor right here, and it's not operating properly. If I've got an issue at that, if I've got an issue at that compressor only, um, then based on how the power flows in this diagram, we know we've got 24 volts. The indoor fan motor is running, so we know it's got power, and we already know it's got power because we got 24 volts anyway if the transformer's in there. We know we got power at the outdoor unit because the outdoor fan motor's running. So what other issues could we have if that compressor's not operating? Anybody? Making you participate this time, dang it.
What is that OL right there?
OL. So that OL would be the internal or external overload on the compressor. So that's a good catch. We haven't talked about that OL yet, right? So on older compressors, especially smaller units, refrigerators still a lot of the times, you'll have an external compressor overload. So we don't know what they're trying to show here, if they're trying to show it external or internal. But either way, a compressor always has an overload so that if it overheats, it's going to cut power to that compressor. So it's a bimetallic switch that opens on a temperature rise and closes on a temperature fall. So basically, anytime it's overheating, it could be drawing too much amperage. If it's locked up, a quick amp draw will cause it to open really fast because the wires inside of it heat up real fast. If it's just running too hot for a long time, so in this case, if the outdoor fan motor wasn't working, that could cause the compressor to overheat, and that'll open the overload until it has time to cool down. or basically anything else that can cause a heat problem. You might even just have it open on a really hot day, especially if it's an older unit or you got a dirty coil or something like that. It could just open because everything's just running hot in general and there's a high load. In general, though, overload opens if you're not cooling the condenser or you got way too high superheat from the evaporator, or you're drawing very high amperage. It'll open really fast. Everything will apply power. The compressor will try to start, but it'll drive really high amperage, and then the overload will open. Um, Sometimes you can keep that from happening by adding a start capacitor. But yep, that overload could be open, and that'll cause the compressor motor not to run for sure. What else?
Capacitor.
Capacitor could be bad on the compressor too, right? This one definitely has a capacitor. So if that capacitor is faulty, it won't operate.
Is the outdoor fan motor running, or is that
Yeah,
off as
yeah.
well?
The outdoor fan motor is running. So we know that we're good on power. We know we're good on low voltage and all that stuff. So um, the overload could be open. The capacitor could be bad. What else we got?
Your compressor. It could be like grounded or bad windings, faulty.
Yep. The compressor itself could be faulty. Um, Side note, bonus one, because there's one more I want you guys to catch, hopefully. But side note, on a compressor, the terminals, the connections at the terminals could be bad. So it could look like everything's tied in good in the control panel, but if you actually go to the wires on the terminals of the compressor itself, something could be wrong with those wires. So especially on a compressor, always get to the compressor and check the actual compressor terminals and make sure you've got good connections there, because a lot of guys will condemn units because they don't come on and it's actually just the wire at the compressor is bad. That that could indicate other problems with the compressor itself, or it could just be a crappy connection. I've seen crappy factory connections at compressor terminals, especially if they got those flag spades that we saw um, when we went over wiring connections. If it's got those flag spade terminals, then the wires can end up rubbing on them and short something out there, and that'll give you a bad wire connection. So that's bonus. There's one more thing that can be wrong though, and what would that be?
Your contactors may not be pulled in all the way.
Yeah, right. The fan motor can be running, and we see that the contactor breaks power to this side of the fan motor, but it doesn't break the power to the other side of the fan motor. So if it's only this one side of the contactor that's having some kind of problem, something's wrong with the set of contacts on it, or the spring's messed up so it's jacked up sideways or something, this set of contacts won't close. So if this set of contacts not closing, we won't get full voltage to our compressor. So it could be that too. But basically, that's the only four things it could be based on this control circuit. We don't have any pressure switches in here. We don't have any other weird stuff that controls this compressor. All it could be is the overload, the motor itself for some reason, wiring connections inside of there, um, capacitor, or one side of the contactor that would be faulty. So you can see, even on something that's really simple like this cooling only circuit, right? Understanding the sequence of operations can rule out a ton of issues if you understand it before you even go to troubleshoot. So that's how you get fast at troubleshooting. Um, as we talk about individual components, remember your sequence of operation. And if you're having trouble picking everything up, then I want you to just go everything A to B, follow the sequence and figure out what's wrong. Test all the individual components until you find out what's wrong. But as you get better at troubleshooting, if you don't do it a lot, or if you are doing it a lot and you're starting to get better at it, always remember your sequence of operation if it's available or you know what it is. And if you know that sequence, you can rule out a lot of components really fast by just seeing what's working and what's not. And I mean, don't get me wrong. A lot of times, if it's the compressor, you're basically going to start it power at the compressor anyway, right? You're going to say, do I got power at the compressor? Is my capacitor good? And and you can troubleshoot the motor itself to make sure the motor is electrically sound, right? But if you don't know your sequence or you don't look at your wiring diagram, you could be missing an important component that would tell you what's going wrong, right? If you don't know about that compressor overload that's inside of the compressor, you might think the compressor's bad when you electrically test it, when if it's got an internal overload, you might be able to wait 20 minutes and that overload closes and then you can get it to run. So you need to think about all the components that are in the circuit, what the sequence is, what should be running, what shouldn't, eliminate as much as you can, and then check all the components that are left on your control circuit for the issues that it could be. And if you're looking at your ladder diagram, you should be able to narrow it down to all the components that might have an issue. So that's why I like to start with sequences of operation, because as you get as you get good at troubleshooting, looking at wiring diagrams and understanding your sequence while you're looking at the wiring diagram can help tell you what to look at when and why. And then you can get faster at uh, sorting out odd problems or something like that, or something where you just don't see all the components immediately or whatever. You can say, okay, well, I know I've got this, I know I've got that. So what's the actual problem here? So with that in mind, I'm going to save this so that I've got it for later. And then um, I think I generally like the sequence of operation on in your book. So you know what, we won't use this one that I've got pulled up. Maybe we'll look at it if there's something else I don't like. But you know what, let me pull actually, dang it. Let me pull that back up. I'll pull up the circuit for the furnace for now. With that in mind, let's go to 3.2.2 heating sequence of operation for a minute. Because with furnaces, understanding the sequence can usually narrow it down to a single component really fast, because everything happens in sequence on a furnace. So once we've ruled out all our basic stuff again, um, once we've ruled out power, voltage at thermostat, so on and so forth, if we're looking at a furnace sequence, then we can usually, once it starts its actual ignition sequence, we'll know what's going on with the furnace. So obviously, if nothing's happening, you got to start back at, do I have power in? Is there uh, a signal at the W terminal or the white wire, depending on how they ran it? Usually your white wire W terminal. So is there power there coming back to the unit? And then what happens from there? But if we read this furnace sequence of, or this heating sequence of operation, um, we'll be able to understand, okay, what's happening when something goes wrong. So let's finish up with that. So 3.2.2 on page 33. Assume that line voltage and control circuit voltage is adequate and available to the unit. To start heating operation in a heat-cool unit, set the room thermostat to heat. Placing the mode selector switch in this position locks out all cooling system functions. Set the fan function switch to auto so that the indoor fan cycle is on and off with the burners. So typically, if we're talking gas heat, the heat controls the fan operation, and it's usually at a different speed. So unlike cooling, where when it powers, it sends power to G to operate that indoor fan relay, on a furnace, it's typically part of the control circuit. So the fan will come on automatically when the system wants it to, based on the sequence, usually at the very end after it's had time to heat up for just a second. So in general, you should not have power to your indoor fan relay and heat on a gas furnace. You won't have power on G. It'll power it through W. But with that out of the way, as room temperature falls, thermostat contacts close, supplying 24 to the coil and the indoor draft relay. In the line voltage side of the circuit, the normally open contacts of the induced draft relay close, applying power to the induced draft motor. Assume that no unsafe conditions exist and the flame rollout switch and the limit switch are both closed. When the induced draft motor comes up to speed and there are no problems, the pressure switch closes to provide power to the gas valve and pilot igniter. The gas valve feeds gas to the pilot assembly where it is ignited by a high voltage spark or a hot surface igniter, right? It could be either one of those, but on this one specifically, they're showing a spark igniter. Um, uh, Once the pilot igniter module verifies the pilot is sufficient to light the main burners, the gas valve opens and the burners light. At the same time, the gas valve is energized. The time delay relay is energized to begin timing. In the line voltage side, the time delay relay contacts are in series with the normally closed contacts in the indoor fan relay and in series with the indoor fan motor. The purpose of the time delay is to allow the air surrounding the heat exchanger to warm up so that cold air is not blown into the structure. Once the delay times out, the indoor fan motor starts and runs on low speed. The normally open contacts of the indoor fan relay isolate the high-speed windings of the indoor fan motor. The unit will continue to run until the room thermostat is satisfied. When the heat thermostat contacts open, the gas valve and induced draft relay are de-energized, shutting off the burners. The time delay relay is also de-energized. Time delay occurs after the relay is de-energized. This allows the indoor fan motor to continue to run after the burner shut off to recover residual heat left in the heat exchanger. So maybe I lied. I don't love that sequence. They left out a couple things. So let me see if I can open up that other sequence real quick. Because I thought this one had it. All right. So how I would scale this out is more like how this one does, because this is more common of your residential furnaces right now. So there's a couple things that the book leaves out that I think are important. Now, with this particular wiring diagram, this is probably how this furnace works, but it's an older style sequence. So generally, I try to remember a sequence that's more like this one. So on this one, while your furnace is waiting for a call for heat, it is in standby mode, meaning it has power, but it is not operating. When your thermostat calls for heat, it will close and complete a 24-volt circuit. On a normally operating furnace, if the circuit is not completed, nothing will happen. Upon completion of this circuit, the pressure switch will be proved open. So on any furnace that has a pressure switch to prove that the induced draft motor is running, is everybody familiar with that? With pressure switches to prove induced draft fan motors?
Yeah, it has those like little tubes attached to it, right?
Yep. So on most residential equipment and even on a lot of your commercial, you always have to prove that the inducer motor is running before anything else can happen. Okay, so it has to say, okay, the draft motor is working. Because if the draft motor is not working, everything's going to overheat like hell and it's not going to vent properly. So one of the first things it does is it proves that an inducer comes on. There's a couple ways to do it. You'll see some equipment that has a centrifugal switch built into the fan motor that proves it's running. Um, it may use some other means to prove it's running, but most equipment you're going to find uses a pressure switch to prove that it's running. So if it's using a pressure switch to prove that that fan motor's running, the other thing it has to verify before anything happens is just like it says that, what is that, step 3 on this thing that we're looking at? The pressure switch has to be proved open, because if the pressure switch is stuck closed, then we don't know the fan's running because the pressure switch is stuck closed. So there's actually a wire that goes back to your heat circuit board that says, okay, the pressure switch is open, then let's apply power to the fan motor, and then let's make sure that the pressure switch closes. So if you start a residential or a light commercial furnace that uses a pressure switch to prove that the induced draft motor is working, if nothing happens on a call for heat but everything is good, don't go to the fan motor first. Go to the pressure switch first and make sure that the pressure switch is not stuck closed, because if the pressure switch is stuck closed, the logic will let nothing happen. And on most furnace modules these days, it has a blinking light, right? And it'll kind of tell you where to start. And a lot of times the pressure switch closed will be one of the blinking lights on there. But if it's not, if they don't give you that, they don't give you that uh, diagnostic code, then you have no idea what the heck's going on and nothing's running and you don't have power to your fan motor and you don't know what's going on. It's the pressure switch is stuck closed. So that's one of the most important things to remember. If it's using a pressure switch to prove induced draft, that pressure switch always has to prove open before it starts running and then close after the fan motor starts running. All right, so starting back at that, upon the completion of the circuit, pressure switch will be proved open. The induced draft motor, or they're calling it the Venner motor here, but the induced draft motor will start and begin the pre-purge process, ensuring there's no combustible gases left sitting in the combustion chamber. The pressure switch will be proved closed. This will run the system through its self-safety test to ensure proper operation. During this time, your ignition system will begin. If you have a hot surface igniter, that'll start to glow. If you have a spark igniter, the spark igniter will start sparking. So you'll either start to glow on your hot surface igniter or you'll start to spark with a spark igniter. Gas valve will open, allowing gas to flow through the venturi tube, where it's combined with air to ensure proper combustion. Basically, the gas flows into the burner assembly, right? Upon combustion, you'll have a flame sensor that will sense ignition and turn the ignition source off. If flame is not sensed, the system will restart and try again up to 3 times. If the flame sensor is not satisfied, or if the flame sensor doesn't prove flame within 3 tries, the unit will lock out. But if the flame sensor senses the flame, then it will uh, continue to burn. All right. After a predetermined amount of time, the blower motor will start, passing air over the heat exchanger to provide heated air. Once the thermostat is satisfied, everything shuts down except for the blower. Um, Sometimes the induced draft motor will run for a short period of time afterward to make sure all the gas is out of the combustion chamber. So that's a post-purge. A lot of especially bigger equipment has a pre-purge and a post-purge on the induced draft. Pre-purge makes sure all the gas is out before it fires. The post-purge makes sure all the gas is out before everything shuts off. Blower fan will run for a predetermined amount of time and shut down, and then the system will go back in standby. So with a furnace sequence of operation, the important things are uh, fan switch has to be proved open, inducer motor has to come on, pressure switch has to be proved closed, then the hot surface igniter, the spark igniter stops or starts. Either it heats up or the spark igniter starts sparking. Then gas is let out of the main valve. As soon as the main burners ignite, there's usually a 2 or 3 second trial to make sure that the flame sensor senses flame. If the flame sensor senses flame, everything's good. So typically your problems can be fan switch is stuck closed, um, a fan switch, pressure switch for the induced draft motor is stuck closed. If that's not stuck closed, then and the blower doesn't come on, nothing will happen. But if the blower comes on and the blower comes on and nothing else happens, and the pressure switch probably isn't closing, so that can be a blocked vent, or it can be a blocked vent, or it can be that the pressure switch isn't operating properly. If that works, your spark igniter doesn't glow, it could be a bad, or hot surface igniter doesn't glow, or the spark igniter doesn't spark, it could be an issue with that. But if that happens and that's good, then you light the main gas. If it doesn't light, then there's no gas to the gas valve or something like that. If the main gas does come on, but it cuts off right after it comes on, then something's wrong with the flame sensing circuit. So basically, every step of a furnace sequence of operation basically tells you what's wrong. You can just see what happens up to a point, and once you get up to that point, you can say, okay, everything was good up to this point, so it's this or this. Everything was good up to that point, so it's this or this. And you basically always end up boiling it down to a faulty board if something's wrong with the board, faulty wire connections, or one or two problems. You can always narrow it down to that. The only thing that's not in this sequence that your book does mention is you're assuming that if you look in this wiring diagram, I'll open that back up. Um, if you're looking at this wiring diagram, the only thing that we haven't brought up is the rollout switch, which is usually located in the burner compartment, and the limit switch, which is the same, which is usually located right there in the heat exchanger compartment. Basically, those are both temperature activated switches. If either one of those are not closed, so the flame has rolled out at some point or something's overheated, then you'll never get power to the pressure switch either. But generally, you can check everything up to that pressure switch. You can check voltage right at the pressure switch to make sure you're getting it before but not after. Um, Furnace sequence of operations pretty important because it's hard to follow all the wires on these furnace boards, and almost all these furnace boards are exactly the same manufacturer to manufacturer. With higher efficiency equipment, some of them are getting a little different, but for the most part, they all have followed the same sequence for about the last 20 to 30 years with only minor differences. So usually, if you know a gas furnace sequence of operation, you're good with almost any gas pack unit you run into. You're good with most water heaters that you run into, if they have an induced draft motor, so like a power vent water heater or something like that. It's going to work almost exactly the same. All these things go through the exact same sequence, and if you know that sequence, you can basically troubleshoot from that sequence. And then you can just, same thing, if you're looking at this control circuit, you can think, okay, what happened in the sequence? Where do I need to troubleshoot? Do I have to look at the pressure switch? Do I have to make sure I got voltage at the gas valve? Do I have to check the flame sensor? What things am I going to check as soon as I don't get to the right point in that sequence? So that's kind of your goal. So, um, is there any questions so far on sequences of operation or troubleshooting based off that sequence of operation? It's a good time to ask questions. If I talk too fast or you didn't understand something, we can go over something again to make sure that you understood everything I talked about. Everybody's good. All right. So, honestly, I think with that, what I want you to do for now is to finish reading everything on sequences of operation, so everything else in that section of the module. And there's some stuff. Next it goes to pneumatic controls. Pneumatic controls are kind of old school. You probably won't run into them too much, but it's nice to read about them at least once. So you should read all those sequences of operation again and try and follow where the wiring diagram goes on the other one. So for instance, with this heating circuit, right, you have W here, all right? Yeah, you have W here, and then that goes across to this whole pilot and gas valve circuit and goes up to the indoor fan relay. In this one, it's saying it powers it on high. A lot of times it never ends up powering it on high. Um, but it'll go through the time delay relay and power low speed on the fan. But that doesn't matter. For now, you can follow W and see what W powers. All right. And then you can follow Y. With Y here, what they're showing is a control board basically. So you'll have a control circuit in here with some logic. A lot of times when you're talking about that, you're talking about it's built into the thermostat, but it could be built into the indoor board. Depends on what equipment you're working on and what kind of thermostat you got. And then you have the G, which just goes straight to the indoor fan relay. And then you got the R off the power circuit. So you got all your terminals off of um, all your terminals off your thermostat. On the thermostat, this is a good way of picturing what happens internally in a thermostat in your head. Are you guys familiar with wiring symbols at all? Did you learn that already? Am I going through it too fast on wiring symbols? Because I'm kind of assuming generally I'm used to like second year being wiring symbols. And since we don't have anything on wiring symbols in this book, I'm assuming you know most of these symbols and can kind of at least guess at what they're at if you don't have to look it up. But seriously, do you guys know wiring symbols?
Yeah, I'm familiar with them in my job and whatnot, but I don't remember us going over them last year.
Holy shit.
I don't remember a
Everybody else?
specific module last year. We're going over wiring diagrams or symbols.
Yeah, I'm kind of on the same page as Jake.
Fuck.
I feel like we
Okay.
talked about them in first year for some reason, but yeah, I'm not entirely familiar.
All right, so maybe what we need to do um let me see if I can find a good way to Google this. All right. Because what we'll probably need to do, wiring diagram, HVAC symbols. Let me see what comes up if I do that. Because there's a few variations on all of them. Is there an appendix in your book with it? That would be nice. Maybe not. I don't see anything. Shit. Show me the picture. Okay. Yeah. So if you look up like wiring diagram symbols HVAC, if you Google that, you should get some images that will help you get a little bit of a head start in the different symbols. And probably look through like 3 or 4 of them, okay? Um, and see how they vary because you're going to have a little variance from manufacturer to manufacturer on wiring symbols. Let me see if I can copy this image and go ahead and throw it in here for now. Document, insert a blank page. Okay, paste. So your most common ones, right, are especially your switches. Make sure that's centered up pretty good. Yeah, so center that screen basically. Switches, closes on fall or closes on or rise. You got pressure, temperature, liquid level, flow switches, limit switches, and differential pressure. Those could look different, but that's a pretty common way to show all those. Over here, you got normally open, normally closed switches, or the other way to show normally open, normally closed switches. You got single pole, single throw, so it's just on off. Single pole, double throw, so it's on or on the other side. Um, and sometimes things will be labeled single pole double throw if it's got an off position also. Sometimes it'll be labeled single pole triple throw if it's got on or an off position. That's getting a little deep, but You got to be careful buying relays and stuff sometimes when you get used to what you're looking for as far as throws. You got double pole, double throw, so like your typical disconnect box with a switch is going to be a double pole, single throw switch. You know what I mean? It's either on or it's off, and if it's on, it's closing two sources of power. And then you got a double pole, double throw switch, so it could turn on power to two different areas. Um, so anyway, you got handoff auto switches. They can show some push buttons, and then there's different ways of showing coils or contacts or something like that. So anyway, you'll want to kind of look these up a little bit, but what I'll try to do is we'll get through we're already pretty much done with sequences. I'll probably talk about them a little bit more in one class because we didn't even get into commercial sequences tonight. And I want to do that a little bit on like a commercial RTU, tell you what that sequence kind of looks like because it's a little different. Um, but we'll go through sequences and then troubleshooting individual components, and then we'll come back to wiring diagrams and see if we can tie all that information together and go over wiring diagrams briefly. But it's only one class per week, so we got a lot to fit in when we do that. So we'll see how long it takes to do that. Because after we get into that, we got to get into troubleshooting cooling and everything else. But it'll get you pretty good. We'll at least have a head start on troubleshooting circuits as far as the other things go. So we can just talk strictly about what's special in cooling, what's special in heat pumps, what's special in gas, and things like that. Um, but anyway, we'll try and do that. So if you guys need a little bit of more information about wiring diagrams, don't let me forget. We need to do a class on wiring diagrams in particular and look at a few different ones and follow them. And like I did with that first picture, um, like I did with that first picture, good practice, especially if you're somewhat computer savvy or something, or you can copy some pages out of the book and use some different colored highlighters. Good practice is to kind of color these circuits just like I did so you can see, okay, where does my red wire go? Where does my yellow wire go? Where does my green wire go? Where do all these different wires go? Where's L1 and L2 or neutral or whatever? Where does all these power, what am I usually seeing in a typical unit that I work on as far as wiring going to these different circuits? And start with residential, unless you do a ton of commercial and you're halfway decent at commercial wiring diagrams and you want to start on refining your commercial wiring diagram experience, because commercial gets really hectic really quick, especially on IntelliPacks and things like that. um, but your carrier ones, your carrier mid-size RTUs are usually pretty dang easy. Your mid-size trains are not too bad. It's just you get like 40 tons and up and they can get real hectic, or you get into Aeons or McQuays or something, it can get real hectic. VRF. So you don't want to start on that. You don't want to try and tackle a hard one first. Make sure you can follow a typical residential wiring diagram and know what all your thermostat wires are and what they do first, and then go from there. And if you don't have any you can pull from, most of you guys live in a house or rent something, rent an apartment. Sometimes even in apartments, you can get to the circuit diagrams of your equipment. Start with your equipment there and make sure you know how it operates. Don't mess anything up, but try and make sure you know how everything operates, or pay attention, take some pictures of some wiring diagrams of some equipment that you've worked on and follow them the best you can, and hopefully that will help you a little bit. But we'll try and do just one class on wiring diagrams and following them and troubleshooting them a little bit more, because you got to do pictorials and ladders. So we'll have to look at some pictorial ones, and I'll probably do them based on carrier, because carrier is kind of the easiest ones to follow half the time. That work?
Yeah.
Yeah, definitely. But when I do mess something up, I'm gonna call you.
Yeah, that's the point. If you guys need something, give me a call. But yeah, if you got any questions, let me know. Otherwise, we're good. I'm going to end this recording and try and figure out where it's saved and see if I can upload this. And then I'm going to try and in the next day or two do another class pre-recorded or something on just just sequences of operation and see if I can expand on it a little bit or fuck it all up and make it complicated, whatever. We'll see how it goes. But anyway, if you're good and you ain't got questions, I'm good. You all have a good evening. If you got questions, speak up.